So we are going to measure regression and prediction intervals. So we are going to do interpretation for 3 types of variation about regression line. Find, interpret coefficient of determination. Find and interpret standard error of estimate for regression line, and construct and interpret a prediction interval for y. So, variation about regression line. There are 3 types of variation about regression line. One is total variation, explained variation, and unexplained. We will cover each one of them. So to find total variation, we need to calculate all 3 of them: total, explained deviation, and unexplained deviation. To remind you, to look here what's happening to figure out about variation, we are going to test to find deviation. Why? Because deviation, it's in the sample represent variation in the population for regression line. So, variation about regression line. Total, let's start with which one? Okay, we know that y bar we know that y bar is average, right? Okay, y, it's observed value, correct? So if we subtract observed value minus average, we are getting total deviation. Okay? Now, if we take predicted y value and predicted minus average y value, that's going to be our explained deviation. So predicted, what we see it's going to be, and what average is now, the difference between them, it's going to give us explained deviation. But difference between observed value y, I, and predicted value y hat is going to be our unexplained deviation. Here it is. Unexplained deviation. All right. So total variation, the word total, we take the variation between, which is a difference between y value and average, right? And the mean of y, and we summarize and square. It's a sum of squares. It's going to be total variation. Wow, this is so thick. Okay. Where from it's so thick coming? Whatever. So, explained variation, it's the same way, a sum of squares of the differences between predicted value, this is predicted value, and y average of value. That's explained variation. Okay? In unexplained variation, it's practically, it's a sum of squares between y value, observed y value, and corresponding predicted value. What we predicted, what the reality is. And you summarize and you square and sum. So sum of squared of the differences. Okay, so total variation practically is equal explained variation plus unexplained variation. Okay. Coefficient determination. Coefficient of determination is the ratio between explained variation and total variation, explained over total. So if we need to use unexplained variation, we take total, subtract the explained, and we get unexplained variation. Yes? And that's we call R squared. That's our coefficient of determination. So, example, the correlation coefficient for the gross domestic products and carbon dioxide emissions data are calculated. Let's say I'll clean this. Is calculated and is R is equal 0.882, correlation coefficient. Okay, find the coefficient of determination. Coefficient of determination. Coefficient of determination is going to be R squared. You take coefficient, correlation coefficient, and squared, you are getting coefficient of determination. So you squared, you get 0.778, which means 77.8% of variation in the carbon emission can be explained by variation in the gross domestic product, because it's explained. Coefficient of determination is explained variation over total, right? That's why we use can be explained, because this is explained variation we are going to use. Okay. Next, standard error. So standard error or standard deviation, we call it's the same thing. Standard because standard deviation it's when we want to find out how far the observed value has drifted away from average. That's an error, right? Okay. The standard deviation of the observed yi values about the predicted value for given xi. The shortly saying, here is the formula of observed value. Sum of yi minus y hat I squared, that's our explained variation, and divided by n minus 2. Okay? N is a number of ordered pair. That's why we are subtracting 2. So the closer the observed values are to the predicted y value, the smaller standard error is. It's just like guessing. The better you guess, the less error is going to be, right? Okay. So here is calculation of standard error, how we're going to do what we're going to do. So we will use it in the example. Here it is. The regression equation for the gross domestic product and carbon dioxide emission data as calculated is let me see. Gee. Let me take this one real quick. We don't need this section because I took material from somewhere else. Is y hat is equal 196.152x and plus 102.289. This one is our intercept, right? We still use mx plus b. This is our b intercept. And this is our slope, mx 196.152. So find the standard error. To find the standard error, we are using a table to calculate sum of squared differences. So let's do it. So here it is, they calculate to use the formulas difference and then square and then summation. So step by step that requires formula where I'm not going to stop because we are using technology just so you know how I would calculate it based on formula. Here it is, the formula. That means y minus y hat divided by n minus 2. If we go back here, y minus y hat, here we have it. See, here is squared, here is just a difference. Okay, and then summarize. At the bottom they summarize there. So after we calculate, get 138.255, it says the standard error of estimate of the carbon dioxide emission for specific gross domestic product is about 138.255 million metric tons, which is a lot. Okay. Next is prediction intervals. A prediction interval can be constructed just like confidence interval. It's going to be constructed for the true value of y in this case, and it's equal, we already see it, y is equal y bar. It's predicted at the value of y minus error, and y bar plus error, where error is equal this crazy formula, T critical, at the standard error S, and the rest we know what is in there. X is our X, the value of X bar is our average. Okay. And we can find a predicted interval for interest for confidence level. So I'm not going to cover this step by step because it's only you're gonna read, but we will use it in solving problem. So construct 95% of interval for the carbon dioxide emission when gross domestic product 3.5 trillion. What can you conclude? Okay. Well, it's the thing is this y bar is given already, this equation, and our n is 10, and we need to know product for 3.5 trillion. That means our x for 3.5 trillion. We need to find out how much will be y hat, which is predicted y. We want to find out value, and then we will do plus. We're going to do plus standard error, y hat, and then minus standard error. Okay, let me see. Oh, here it is. So we are adding, subtracting here, y bar, y hat, subtracting error, and y hat, adding error. And we are getting for 95% confidence interval, we are saying that for 3.5 trillion of gross domestic product, the carbon dioxide emission will be between 439.397 and 1138.245. Okay, looks like we got to summary. So we covered 3 types of variation: total, explained, unexplained. Coefficient of determination, found the interpretation of coefficient of determination. That's a square of the correlation coefficient. Standard error, it's a standard deviation, how far it's drifting away from the average, right? And we learned how to calculate prediction interval, which realistically you are not going to calculate, but use technology for that. Okay, we are moving to multiple regression. So we are going to learn how to figure out standard error of estimate, find multiple regression equation, and the coefficient of determination. So we are going to use multiple regression equation to predict y value. So, multiple regression equation. In many instances, a better prediction can be found for a dependent which we call response variable, by using more than one independent. So it's crucially important. More than one independent, so that's what makes it multi-regressional equation. So we have several x's and only one y. So y is our dependent response variable, and independent explanatory, those are several x's. For example, a more accurate prediction for carbon dioxide emission discussed in previous sections might be made by considering the number of cars as well as the gross domestic product. As you remember, we were doing example in previous recording that how CO2 depends on domestic gross product. But we can include in that also amount of cars, because the more cars, the more emission, right? Carbon dioxide emission. So let's see what we are going to do in this case. So the model for multiple regression equation is this one. Y hat, that's our responsive variable, is equal b, which is going to be our intercept. We are following y is equal mx plus b, so this is our b. M1, x1, those are all slopes with axes, because remember we said we can have several axes. So it's going to be x1, x2, x3, xn, x1, x2, x3, blah, 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 xn. Those are components of x, right? With their, accordingly, with their slopes. So m1, m2, m3, and mn, xn, okay? So, it says here, x1, x2, x3 are independent variables, b is y-intercept, and y is dependent variable. Okay. Example, finding a multiple regression equation. So, what we're going to do here? A researcher wants to determine how employee salaries at certain company are related to the length of employment. So how does it work? The longer you work, the better money it is. Previous experience, also based on previous experience. So length, previous experience, and education. I see here x1, x2, x3. Several three independent x2 and x3, three independent variables. The researcher selects 8 employees from the company, it's a sample size n, and obtains data shown on the next slide. Okay, here they are using Minitab, we are not using because our software is .crunch. So, finding the multi-regressional equation. So those are employment. Let's say employment here we get Okay, employment, then experience and education, and we see how it's going to affect the salary. So it's going to affect based on multiple regressional equation. So we are going to solve it. So it shows where to enter. We don't need to go over this because we are not entering into mini tab or anything. So I'm skipping this. All we're gonna get is our, here we go, regressional equation. Trying to clean this. Okay. So what do we get? 49,764, this is, it says here constant, which is going to be our intercept. X1, it's 364, X2, 228, and X3 is 268. So we're going to get all this information also based on our software, StatCrunch. So we are going to predict also Y value. How are we gonna predict Y value? After finding the equation of the multiple regression line, you can use equation to predict Y values. Once we have formula, it's already algebra. Once we have formula and X is given, we can, all we can do, plug into this value of X we have and find out predicted Y value. Okay? Pretty straightforward. So here it is. We have a regression equation here, and we need to predict employee salary given 12 years of current employment, 5 years of experience, and 16 years of education. So that's exactly what we're gonna do. Plug here, instead of X1, we plug 12. Instead of 12, instead of X2 experience years, plug 5, and instead of years of education, plus 16. Multiply, summarize, and we get 59,544. So, using technology, we are going to use technology to find multiple regression equation, the standard error of estimate, and coefficient of determination. These three things. And we will use also multiple regression equation to predict Y values.